What's up, guys? So today we'll be covering a topic called managing complexity. Now, the material we're covering today actually applies more broadly in the field of machine learning, but I'll cover the material from a general perspective and then refer to the specifics as they pertain to tree-based methods, since we're still in the tree-based method section. But you'll probably find it useful to revisit this lecture at a later stage because, like I said, some of what we're covering here actually applies to other algorithms as well. So let's jump into it. Cool, so we've seen how our recursive binary partitioning algorithm provides us with a simple yet powerful tool for extracting patterns from the data, right? And we've also seen that the resulting decision trees are useful for interpreting the data. But as I alluded to earlier in the course, there's more to machine learning than just fitting a model or using an algorithm. Okay, and indeed, the particular algorithm that you use is only half of the equation, perhaps even less if you ask the right person, right? Right, so to see this, recall that at the start of the course, I said that the science of the machine learning is concerned only with whether learning is feasible or not. Okay, now we've developed an excellent learning algorithm here, but we haven't addressed the learning aspect of it in the true sense of the word. Okay, now doing so involves some abstraction. So what we're going to do is I'm going to list some fundamental assumptions of machine learning, and then we're going to build our arguments around that. Okay, so first assumption. An unknown pattern exists which generates the data. Okay. Second assumption. We cannot come up with a mathematical expression for that unknown pattern. Okay. 3. We have lots of data points. Okay. So, and this means lots in the relative sense, not lots as in it's a lot for me to store. Okay. That is a very important concept when you consider asymptotics later on. Okay. And then 4, if there is any noise, it is not a dominating component of the system. So i.e. the signal to noise ratio is favorable. Now, I've put an asterisk on this last one because it's one that I've tagged onto the original list because I feel that it's a subtle point that's often missed and you should sort of learn it as you go on, but we might see it creep in at a later stage. And then I'll refer back to assumption 4. Okay, right, so under these assumptions, the learning problem we have can be summarized very loosely as follows, right? What we want to establish is, given a finite set of observations, so that would be assumption 3, whether the unknown pattern can be extracted from the data. So the unknown pattern being assumption 1, right? So note that no mention here is made of any particular learning algorithm. As it turns out, the learning algorithm is just a tool that we can potentially use to extract the pattern when assumption 2 applies. Okay, right, so to see why this presents a problem for what we've been doing up to now, it's probably best to consider the workflow of a machine learning application. Okay, so let's go. I give you a data set and I task you with producing an algorithm which can accurately predict a response for some feature inputs. Okay, you use, for argument's sake, the recursive binary partitioning algorithm to arrive at the decision tree for this data. You bring that back to me. I then ask you, is this model any good? Okay. You then give me a metric for how accurate the model is by checking how well it predicts the responses in the data that you've used. Okay, and therein lies the problem, right? The observations you're using to judge how well the model is doing at its prediction task was used to fit the model in the first place, right? So we should expect our model to actually perform pretty well, given that it's actually seen those examples, right? But when you were tasked with producing an algorithm that can actually predict, what we mean is predict for unseen data, right? So as such, we actually need to distinguish between data which are in sample, so those observations which are used to fit or train the model, and data which are out of sample. Okay, so new or unseen data which our model is actually used to give predictions for. Okay, so very important distinction. Right, and as it turns out, answering the question of whether learning is feasible or not is actually quantified by the ability of your model to generalize to unseen data. Okay, as a consequence, even though our algorithms typically aim to minimize some objective function based on the in-sample data, the goal of learning in the true sense of the word is to minimize the so-called generalization error. Okay, or basically our performance on the out-of-sample or unseen observations. Okay, now again, we can make this more concrete using some very interesting mathematics, and we cover this in Masters, but in a nutshell, our job is to, whatever model or algorithm we use, we need to do our best to ensure that our model generalizes well to unseen data. And that's got very little to do with the in-sample performance of a model and everything to do with the out-of-sample performance of a model. Cool, so as it turns out, the ability of our model to generalize or minimize the generalization error based on a finite data set is very closely linked to its complexity. Okay, now this link is often explained at the hand of the so-called bias-variance trade-off, which in turn is quantified by an equation which links the out-of-sample performance of a model to its behavior over multiple draws of a data generating process. Okay. So to demonstrate this phenomena, what we'll do is we'll conduct a simple experiment based on a synthetic data generating process so that we know what the true underlying pattern is, and then we'll simply use tree-based models to try and extract this pattern. Okay, so we set up a simple experiment based on the fundamental assumptions of machine learning, and then demonstrate the link between complexity and learning. Okay, if we keep that equation in mind. Okay. Right, so particulars of our experiment. For the experiment, we'll have a single real valued feature or predictor, and then a single real valued response. Okay, we'll then fix the underlying pattern to be a simple square wave pattern, so that our tree-based method should theoretically be able to extract that, and then add some noise to that just to make sure that there's some variation, and then we'll make repeated draws of the data generating process. Okay. So each draw of the data generating process is a realization of the data. Right, so at each realization of the data generating process, we apply the recursive partitioning algorithm, and what do we see? The decision trees vary quite substantially over each draw. Okay, but that's not good for learning, right? What we want to see is the trees replicate the underlying pattern, or at least something close to it. Okay, and indeed, this sort of demonstrates a flaw with the tree-based methods in that they suffer from so-called high variance. Okay, so the models vary quite substantially based simply on the data that it sees. Now, why this happens? This follows both from the fact that erroneous splits early in the data, based on the data that it's seen, are sort of carried forward in the model. It's a sort of nested algorithm. But also the unbridled pursuit of minimizing the objective function in sample tends to have these models overfit the data. Okay, that is that the decision tree produced will typically have too many nested decisions, so i.e. a large tree with many nodes that only serve to replicate features that are unique to that particular data set that it's seen, and not the underlying structure. Okay, so as a consequence, if we had to quantify how well our model was doing at each realization of our data generating process, we'll find that based on in-sample data, it's doing brilliantly, right? But on out-of-sample data, we'll see a significant drop in performance. Okay, so the phenomena really manifests as a large discrepancy between the in-sample and the out-of-sample performance of the model. Okay, because the resulting decision tree is simply too complex, with too many splits serving to replicate features which are not the underlying structure, but rather just variation in the data. Okay, cool. So how do we fix this? Well, if the problem is complexity, surely we need to rein in the decision tree and produce a simpler structure. Okay, so indeed what we'll do for these purposes is resort to the so-called cost complexity pruning. So this is a process by which we fit the tree using the usual recursive partitioning algorithm, but we modify the objective function to include a penalty term. Okay, and this penalty term will typically grow as the complexity of our model increases. Okay. Now this has the effect of effectively constraining the minimization of the objective function, and thus sort of forces a suboptimal solution, which then produces a simpler tree. Okay. Now another feature of this penalty term that we add on, it will have a so-called tuning parameter. Okay. So what that tuning parameter allows us to do, as its name suggests, is sort of modify the amount by which we penalize the underlying objective function. Okay, so we can actually, turn up that parameter or turn it down based on how much we want to actually penalize the objective function. Okay. Now, a very interesting thing. As it turns out, modifying the objective function in this way has the effect of producing trees which are in fact nested within the tree produced by the unmodified objective function. Okay, so that is if we start out with the unpenalized objective, we'd get a large and complex tree. But then what we can do is, if we were to sort of post hoc modify the objective function and see where we end up, we'll end up with a simpler tree nested within that complex tree. Okay, so this essentially has the effect of sort of trimming back or pruning back the branches of the tree to a simpler structure in that more complex tree, and hence the name cost complexity pruning. Okay, right, and the fact that we have a tuning parameter allows us to actually manage the complexity of the tree produced by our model. Okay, so in summary, we can actually manage the complexity of our tree-based model by varying the tuning parameter. Cool, so to demonstrate how varying complexity affects our out-of-sample performance, we'll consider our synthetic experiment again. Okay, we'll repeat the experiment from before using the exact same draws of the data generating process, only this time we'll constrain the partitioning algorithm in such a way that it produces trees with at most 4 terminal leaf nodes. Okay, so something simpler than we've seen before. Right, and as you can see, the tree structures vary substantially less over repeated draws of the data generating process after we apply the constraint. Furthermore, on average, the discrepancy between the in-sample and the out-of-sample performance is substantially reduced. Okay, this is great news if our goal was to learn the underlying pattern, right? Indeed, if we compare the fitted models to the true pattern under each configuration of the experiment, so the previous configuration being the unconstrained trees, and then the current configuration being the pruned trees with 4 terminal nodes, we see that the pruned trees more closely replicate the underlying pattern, whilst the full trees quite obviously replicate features which are unique to each dataset. Right, and this brings us closer to our goal of learning. Okay, so pruning our models. Now there's a caveat to this. Okay, so obviously if we constrain the algorithm too far, okay, the resulting decision trees could be too simple, so i.e. not complex enough to actually extract the underlying pattern. Now, to see this, recall that if no split is applied, the fitted value for any coordinate in the feature space is simply the in-sample mean. Okay, now under the assumption that there is a pattern in the data, there is no way we expect such a model to outperform even a simple decision tree or model. Okay, and this actually demonstrates the sort of trade-off aspect of the so-called bias variance trade-off, and that is that we need to rein in the complexity of our models in order to avoid high variance, but we also need to not constrain them so far as to render it impossible for the model to actually capture the pattern in the data. It still needs to be complex enough to actually replicate the pattern in the data. And indeed, in the real world, we'll be applying this. It's possible that pattern is going to be quite complex. Okay, so how do we find an appropriate trade-off? Well, if we look again at our equation, which decomposes the out-of-sample error in terms of the bias and variance, in an ideal world, what we could have done is maybe just evaluate the elements in the right-hand side of that equation and thus quantify the bias and variance exactly, right? That would have been cool. Evaluate the bias, evaluate the variance, see how they vary in terms of complexity of the model, and then find the balance. Okay, now we'll actually do this in masters, but if you actually look at those terms quite closely, you'll find that at least one of them involves knowing the underlying pattern. Okay, and one of our assumptions was that part is unknown. Okay, we don't know the pattern. Okay, so we can't do that. We can't evaluate the right-hand side of the equation. But because it's an equation, okay, we can try and approximate the left-hand side of that equation using something called the validation set approach. Okay. Now, right, very important. This is the most important aspect of any machine learning application. Okay, the validation analysis. Indeed, any machine learning application which is not accompanied by a proper validation analysis, the predictions for that should be considered rubbish. It does not matter how cool the application is or how exciting the predictions look. If it's not accompanied by a proper validation analysis, you have not demonstrated that your algorithm has learned anything, period. Okay. Even though the validation analysis is only a useful approximation in establishing whether learning has occurred or not, more on this is masters, it's got to do with approximating the left-hand side of that equation, it is the only view we have into learning under the present learning paradigm. Cool, so what's a validation analysis then? Okay, now recall that our aim is to find a model which generalizes well to unseen data, and that we've quantified this in terms of the out-of-sample error. Now the purpose of a validation analysis is to approximate the out-of-sample performance of our model based on a single realization of the data generating process. Now, everything we've discussed up to now keeps alluding to multiple realizations of the data generating process, when in fact in the real world we only have a single realization or single data set. Okay, indeed, going to the left-hand side of our bias variance equation was rather clever, but it doesn't actually get us around the fact that that equation actually integrates over multiple realizations or all possible realizations of the data set. Okay, so you see why the mathematics is interesting and why you need to be doing honors and masters with us. Right, so what we do is as follows. We create an in-sample and out-of-sample data sets, and by simply splitting the data into an appropriate ratio. Okay, so typically this is 50-50 or 70-30 or something like that. Okay, the in-sample data set or training data set will then be used to fit whatever model we have in mind, and then the out-of-sample set is then broken up into two further sets. Okay, the first set is called the validation set, and the second set is the so-called test set. Okay, now the validation set is then used as a proxy for unseen data under various configurations of our tuning parameters, right? So in order to determine appropriate complexity control for our algorithm. Okay, so loosely speaking, the validation set is used to approximate the out-of-sample performance as the complexity of our model is varied. Okay, so we thus typically measure the validation error of the model for a range of values of the tuning parameter, and find the appropriate value for the tuning parameter as that which corresponds to the minimum of the validation error. Okay, so based on the validation set. Okay, and this follows since, according to the bias variance composition, this will be the point at which the appropriate trade-off is achieved. Okay, now what happened to the test set? Okay, now as the name suggests, the test set is used to test the performance of our model under the premise that it has learned. And remember that our learning here involves managing complexity. Okay, so hang on. We just did that using the validation set, right? Well, actually, no. So to see why this is, recall that we need to assess how well our model is doing based on out-of-sample performance. Okay. Now, because we've used the validation set to vary the tuning parameter of our model, it is in fact contaminated by that information. Okay. As such, to get an independent measure of how well our model's doing out of sample, we need a set of observations, i.e. the test set, to check our work. Okay. Now I cannot stress this following point enough. Okay. When you put aside the test set, okay, you should mark it as do not touch until you are absolutely sure you are done, and you have to be absolutely sure you're done before you touch it. Okay. Indeed, you're only allowed to use it once. Okay, and I mean once. If you check your work, go back, redo the validation analysis, and check it again, your analysis is void. Okay, because the moment you touch that test set again, okay, your model is contaminated by that information. Okay, so you really need to police yourself. The moment you touch that test set twice, you're fooling yourself. Okay. And in any case, if you're going to be ignorant about this, well, presumably your model is going to be applied in the real world, where it will be subjected to truly unseen observations, and your predictions will be rubbish anyway. Cool. So what's the story with cross-validation? Why is this in our notes in software? And what's the difference between cross-validation and just a validation analysis? Okay. Well, there's quite a bit to this, but I'll just give you an intuitive explanation. Okay. So one rather obvious issue with breaking up the data in this way is that the statistics we calculate, such as the validation error, are still subject to variation, right? So I mean, which observations end up in the validation set is rather arbitrary, and any permutation of the training and validation split is just as valid, but would have produced different statistics and hence different complexity controls based on how the data was varied. Okay. So what cross-validation does is it allows you to conduct multiple training and validation runs. Okay. So this is simply achieved by breaking up the data set into K sets or folds. Okay. K minus one of these folds are then used to train the data, while the remaining fold is used as a validation set. Okay. And then what you do is you permute through sort of, all K iterations of that to get K different training and validation runs. Okay. So what's nice about this is, this gives us control on the variation because, we can aggregate that information to get a good point estimate of what the validation error is. But more importantly, we can also measure how much it varies by calculating the standard deviation, say, of the validation errors over our multiple sets. Okay. So whenever we calculate the validation error, we can then place confidence bounds around where the true validation error is to get a better idea of, say, where the minimum on that validation curve is, for example. Okay. And that's the idea and the magic behind cross-validation. It sort of uses the validation set approach, but then also takes care of the variation aspect of it, even though we have only a single data set. Cool, so that concludes the theory for the validation analysis, and we'll revisit this with the neural network section again. But we still need to answer the question, right? How do you conduct a validation analysis for tree-based models specifically? Okay. Well, one of the problems with this approach in the context of tree-based models is that the complexity of a tree varies discretely. Okay, so we don't get a nice smooth validation curve, right? So that is, the validation error is not actually a smooth function of the tuning parameter of the partitioning algorithm, right? So it makes it difficult to assess where a minimum point along that validation curve is and find an appropriate bias variance trade-off. Okay. So instead, what the software used to fit these models in practice actually do is they measure the deviance for trees of increasing complexity. Okay. So now recall that the deviance compares the model fit relative to a theoretically perfect model, so i.e. one which predicts the data perfectly. And as such, as the number of leaf nodes increase, we expect the tree to come ever closer to this model and thus observe a drop in the deviance as we increase the complexity. And we'll see that happens discretely, right? So what we do is we plot the deviance as a function of the number of leaf nodes, each of which will correspond to a range of values for the tuning parameter. So we'll plot those on a different axis, and then we'll observe a systematic drop in the deviance, okay, which eventually flattens out as incremental improvements in accuracy decrease. Okay. So in order to actually decide on an appropriate number of terminal nodes, what we need to do is look for a minimum point or a point along that curve where it flattens out, and then we read off the appropriate range for the cost complexity tuning parameter, and then apply this to get the appropriately tuned tree, okay, or pruned tree. Right. But what does this have to do with cross-validation or validation at all? Okay. Well, as you will see, when we use good software to actually conduct cross-validation for a tree model, it will not only report the deviance at each point along the complexity scale, but it will also provide confidence bars around those points, which are in fact constructed using cross-validation, right? So that's why you need to understand how cross-validation works. Okay. So in practice, what we actually do is we invoke Occam's razor, or the principle of parsimony, and we pick the simplest model, which is within one standard deviation of the minimum deviance along that curve. Okay, so we use those error bars to read that point off. Okay, right, so What that means is that for future reference, when I ask you to conduct a validation analysis for a tree-based model, I'm actually asking you to produce this plot, right? So, plot the deviance as a function of the tuning parameter, use the cross-validated results in order to pick appropriate level of complexity for your decision tree, and then continue the analysis from there. So in that way, I know that you've checked that your model actually generalizes well, and you've used the validation analysis to do that. Okay, cool. So I hope you guys found this interesting. In the lab session that follows, we'll look at how this is applied to some real-world data, and then we'll move on to the model mechanics for neural networks. Cool. Cheers.